Alicia Plinio and Patrick Granitzki will be presenting a presentation on displacement piles, helical displacement piles, as an alternative to conventional driven methods. Patrick, floor is yours.
Thank you, and I'd like to thank DFI for giving us the opportunity to present. This presentation was originally presented during the 47th Annual Conference on Deep Foundations in Maryland. My name is Patrick Granitzki, and I'll be presenting with my colleague, Alicia Plinio. Our presentation will cover the advantages of providing alternative pile types in comparison to the initial bid package request in order to save the client time and money for the project. And as you can see, our title is high capacity drilled helical displacement piles as an alternative to conventional driven methods. For some project background, our project was located within the Red Hook district of Brooklyn, New York, which included the construction of 2 buildings within an existing affordable housing community. The development was a result of Superstorm Hurricane Sandy, which impacted the Northeast, causing flooding in many of the local communities, including our site, as can be shown on the photos on the slide. The area of Red Hook housing was classified as a flood zone following Hurricane Sandy, which brought heavy flooding up to 6 feet. The flooding resulted in major damage to the Red Hook houses, including the support structures for utilities. The basement level of these housing facilities were flooded, which impacted the mechanical rooms and utilities, which were vital to the people living in the building. The west building proposed was a 2-story structure to house a majority of the affordable housing community's new utilities and mechanical controls, while the eastern building was a 5-story structure that included a combination of both utilities, services, office space, and amenities. The subsurface investigation was performed by a geotechnical engineer of record, and the site was located within New York, as can be seen on the map on the slide. The published geological conditions for the site generally included glacial till material, which was a combination of silt, clay, sand, cobbles, and boulders deposited. For the subsurface investigation that was performed by others, it was a series of SPT soil borings throughout the building pad areas. As you can see, the western portion had a series along the perimeter of the building layout, as well as the eastern building. The subsurface conditions within the western building generally included an existing fill material underlain by an organic stratum, a very loose to dense silty sand stratum, and finally a sandy silt and a soft, loose, generally grading to a hard and dense condition. So we can see the geotechnical challenges for the site, and the type of building wouldn't preclude the use of a conventional shallow foundation system. For the eastern building, again, there is an upper existing fill material underlain by a very loose to medium dense silty sand with a clay silt lens that was a soft to hard consistency, followed by a silty sand in a very dense condition. Next, I'm going to hand it over to my colleague, Alicia Plinio, who's going to go through the pile load requirements as well as our design.
Do I have control? There we go. All right. So for the western building, the 2-story lower load building, it required a 64 kip compression load, a 1.5 kip lateral load, and no tension. For the eastern building, which is that taller 5-story building, it was a 210 kip compression, 60 kips tension, and 20 kips lateral. So the bid documents were prepared before we came onto the job, and they had proposed pile systems in those bid documents. So for the eastern building, so that higher capacity building, they proposed an 18-inch diameter open tip pipe pile driven to 110 feet below ground surface. For the western building, they wanted a 16-inch diameter, 35-foot long conical tip driven pipe pile. So we worked with the contractor, we'd worked with this contractor before, and they came to us and said, we think that this pile might be an alternate to those driven pile systems. And they wanted to use a drill displacement helical pile. So as you can see in these pictures, it's similar to a conventional helical pile, except that through the tip of the pile, they're pressure grouting to form a grout column around the shaft of that pile. So this picture on the left is an example of, here's that pile. You've got a grout hose coming through, and this rig both drills the pile in and pushes the grout through. Another picture of the rig. So when we do our design for these types of piles, we kind of do a combination of methods to determine the estimated capacity. So we do a combination of a typical helical pile, so basically with the plate factors, and then we do a typical micro pile. So basically the bond values of that concrete shaft. So a combination of the two is how we're getting that estimated capacity. Here's a quick breakdown of our sheet just to show we're using the bond strength and the end bearing factors from the helical plates. We also neglected the fill in the organic layers for our design. So for the western buildings, this is the lower capacity building, or the only 2-story building. Again, we're trying to achieve the 64 kips compression, 1.5 kips lateral. And we came in and designed a 4.5-inch diameter shaft with a 14-inch helical plate drilled to 45 feet with a grout column around it. So we then came in, we installed 4 test piles. The resistivity the resistance in the ground from the monitoring system. So we've got grout pressure, torque, grout monitoring. From all of this data, we actually terminated a little bit shallower than our anticipated depth. So from our design, we thought it would be about 45 feet. We looked at the data that we're getting in the field and terminated between 38 and 42 feet. We then came in and we performed lateral load testing and compression load testing. So for the lateral load test, we tested it to a little bit more than 2 times the required capacity. So we were supposed to go to 3 kips, but we overshot a little bit. But even so, at 3 kips, which is the ultimate capacity, we were at about 0.4 inches of deflection. And at our ultimate, which was about 3.5, we were still under 0.5 inch of deflection. Then we came through and did a decent amount of compression load testing. So we were looking for 64 kips for design. We tested to 128 kips. Also, we were in New York City, which for anyone who's done any compression load test in New York City, you're required to have a 24-hour hold or a 12-hour hold on your ultimate load. So we held these ultimate loads for at least 12 hours. And if there's any kind of movement, we have to hold them for longer, up to 24 hours. So we came in, we tested everything. We just did 4 load tests, and our deflections on our 4 load tests were our settlement range between 0.36 and 0.52 inches at our ultimate design, or at the ultimate load. So then we came in and we designed the piles for the east building. So this is the higher capacity 5-story building. So we needed 210 kips compression, 60 kips tension, and 20 kips lateral. So we put together, because we needed such a high lateral load and we were using such a relatively slender shaft, we came in and we're compensating for that lateral load with an upper cased section on this pile. So you could see in this sketch, we've got a 20-foot long cased section that's an 18-inch diameter, 500 wall thick, or 0.5 inch thick, and it goes down to 20 feet. Then we slide through there, the helical pile, grounding the whole way down. And that helical pile is a 16-inch diameter plate with a 5.5-inch diameter with a 5.5-inch diameter shaft. And we estimate that we were getting a 7-inch diameter grout column. Based on our calculations, we thought we would need to go to about 50 feet below ground surface to achieve these capacities. So then we got out there and we put some test piles in the ground. This is what our upper cased section looked like. So this was the 20-foot long, 18-inch diameter upper case section. It has a very small, as you can see, a small helical plate on here. The point of this is just to allow it to advance through the cobbly fill that was on site. So it's got some teeth, a little helical plate just to get it into the ground. Again, based on the monitoring that we had on site, we ended up terminating the piles at varying depths. So between 42 and 52 feet, depending on what we were seeing out there. And here are just some pictures of the installation. As you can see, we installed that case section first and then slid our helical pile through it. And then we did some load testing. So we built up a pretty nice little frame. It was in the springtime. So we had some pretty wicked fluctuations in temperature. So we tried to keep the frame pretty consistent since we were out there for at least 24 hours. So they actually created a heated tent for us, which I will say was pretty nice instead of freezing your butt off at night. So this is a picture of our load test setup. We've got dual jacks in there to be able to achieve that higher load. And so the first test that we ran was a lateral load test. So we needed 20 kips lateral and for design, and we tested to 40 kips ultimate. We performed 2 lateral load tests, and the ultimate deflection at the ultimate load ranged between 0.44 and 0.47 inches, which was below the requirements that the structural engineer provided. We then came through and did a pretty decent amount of compression load testing. So we needed, again, 210 design. We went to 420 ultimate. We performed 4 different load tests, and we saw varying settlement between 0.48 and 0.73 inches. We also then took our worst case load test and wanted to see what kind of ultimate load this pile could really achieve. So 420 was our ultimate based on design. We loaded that up, brought it back down so we could have 1 complete load test. Then we pushed it back to 420, and we saw where we could get it before either our frame would be at its capacity or the pile. This was the capacity of our frame, but it also looks like that pile started to run. So it was probably also the ultimate capacity of this pile. So I was at 678 kips, and that was 1.39 inches. We got 1 inch at about 570 kips. So you could see we probably could have pushed this pile a little bit harder. So when you compare the piles from the bid documents to the piles that we ended up installing as an alternative, for the west building, we initially, the bid documents wanted 16-inch diameter, 35-foot driven conical pipe piles. We came in and ultimately installed the 14-inch diameter helical plate, 4.5-inch shaft with a grout column to 38 feet. When my client compared the cost of these piles to a driven pile, there was still significant cost savings, even though we were a little bit longer in depth than that 35-foot driven pile. Then for the east building is where the really significant cost savings came in. So the bid documents wanted a 110-foot, 18-inch diameter open-end driven pipe pile, as I said, driven to 110 feet. Our solution with that 60-inch diameter helical plate, 5.5-inch shaft, and that upper 20-inch case or 20-foot case section was drilled to 40 to 42.5 feet below ground surface to achieve the same required capacity. So significant savings in depth, but then also some other savings in material time and noise. So when we compare the alternates, our client saved millions of dollars in foundation installation. They saved significant money in materials and labor and productivity. They also altered the project timeline that was anticipated when driving piles versus drilling these helical piles. They ended up coming in with a shorter project timeline. They also removed the need for vibration monitoring at the project, since this is a drilled pile and had minimal vibrations. So significant cost savings there. It removed the need of splicing. So especially those 110-foot piles would require splicing. These piles are bolted connections. So simply bolt that connection together, keep pushing it in the ground. It also is significantly quieter than a driven pile, which I'm sure the residents of these apartment buildings really appreciated. Lessons learned: that newer tech, we had a lot of pushback because we were fighting up against a tried and true driven pile. This is a newer pile system, especially for New York City, and we got some pushback. So we went through, we did some significant load testing to make sure that this system would perform as well as the driven pile system. But ultimately, we were persistent, we were patient, we educated the client. We also had really good test results, and that allowed the design team to ultimately accept this pile and allowed this new product to be used for their project. All right, any questions?
Thank you for this presentation. Interesting application of a different pile type foundation. We have a few minutes, so you said at the very beginning, it was either you or Patrick, that this pile type was suggested by the contractor. It did not necessarily come from you, as it suggested that this is going to be suitable for this project. Was this the first time that you used this pile type yourself? And if so, how do you look at this pile type now? Do you see much wider applications? Are you suddenly very enthusiastically supporting helical piles? How did it develop? And then how did you consider this pile type?
Sure. So we have a relationship with this contractor. And so they talked to us about this possible solution because they had seen it used on another site. And that's the reason why they pulled us into this job. So this was just a really good solution. It ended up being like all the stars aligned. We had the relationship with the contractor. They had this understanding of this pile type and knew that we could assist them on this job. As for the use of helical piles, are we all gung-ho on the use of them everywhere? It's specific projects make more sense. We also really try and push for the grouted helical piles instead of just a plate with a slender shaft or a larger helical pile. I know helical piles are typically those very slender shafts with plates. So we're getting into the bigger helical piles and the grouted displacement helical piles. And they're definitely getting wider acceptance, especially in the New York City region, which New York City has a lot of restrictions on just helical piles in general. So it takes a little convincing to get the DOB and to get the project teams to agree that this pile isn't strictly behaving as a helical pile. But it's definitely seeing wider acceptance, and we're seeing more projects with this type of pile on it.
But this pile type is considered a helical pile under the New York City Building Code.
It is a gray area. Depends on who you talk to. It depends on the story we're trying to tell.
Right, I can see that. One other thing that struck me was you mentioned that the installation of these piles varied between, I think it was 40 and 50 feet or something like that.
Yep.
How did you, when you said it was based on monitoring data, what did you monitor? The torque to figure out what the installation depth was? How did you do that?
Yeah, so we monitored the torque as it was being installed. So we had a minimum depth that we were trying to hit. And if we saw very low torque values, we would slightly push it to make sure that we were in a solid stratum. If we saw very high torque values at like that 42-foot pile had torque values that were almost at the extent of the rig. So we called it there and then we tested that. And then I think we had a second one that was about the same depth, just so that we could replicate that and not have it one pile that was extremely short terminate just on that material. So in this one area of the site, we found that at that stratum it was very dense and very difficult to get through. And instead of fighting our way through it, we just sat in it.
Oh, okay. You said you prefer a grouted helical pile more than the standard helical pile. Question, of course, is when you grout a helical pile, you put grout down, you don't really know where it's going. It's very hard to figure out what kind of grout layer you get around the pile. Can you share your thoughts about that whole issue about how do you control the grouting of this type of pile?
Yeah, that's a great question. And that was one of the pushbacks that we had in the approval process for this pile, for this particular site. So we ended up using a very conservative grout column for our calculations. So it was no more than 2 inches of grout that we assumed around the outside of the pile. So for the 5.5-inch diameter shaft, that larger capacity pile, we assumed a 7-inch diameter grout column. For that 4.5-inch diameter shaft, we used, I believe it was a 6.5-inch diameter grout column. So relatively conservative. When we pumped our grout, we did our grout volumes and kind of tried to figure out, well, what does that pile actually look like based on the volume we pumped into the ground? We were getting somewhere around 12 to 14-inch diameter grout columns for both piles. For the smaller diameter piles, since it did not have that upper case section, they did end up excavating probably about, in some spots they excavated up to like 10 feet of that upper pile for, digging pile caps, things like that. And we could see that in those areas that our calculations from our grout volumes were pretty accurate. So we were pretty conservative on those grout volume or for the grout columns, and that gives us some ease of, we understand that it's not constant, it's dependent on how much pressure is being pushed down there, what the stratum looks like. So we know that it probably undulates throughout the entire profile of the pile, but we're pretty conservative to make up for that on our grout column calculations.
Okay. Last question, at least for now, until we come to the Q&A. You said it's for one of the piles or one side of the piles, you put a case section at the top to provide more lateral strength. Obviously, you got much more lateral strength than what you really required. How was it a surprise, or did you just put in this case section with the idea that, hey, better safe than sorry? Or was it a question of, hey, suddenly you thought you would be much closer to what you would be getting? Can you say something about that?
So we wanted to be, we'd rather be safe than sorry for this lateral load. We looked at using a smaller casing up top, like a 16-inch or a 14-inch, but we also needed to make sure that our helical plate could get through that casing. So our helical plate was if I'm remembering correctly, a 16-inch diameter. So we had to have a casing that was at least big enough to allow that helical plate to get through. So that kind of governed how the diameter of that upper case section. And then it was just kind of based on availability. So this job was installed in 2021 when steel was a little bit difficult to get. And so the availability of this 18-inch, 0.5-inch diameter or 0.5 thick casing just happened to work out really well. And so that's what the contractor wanted to use. We probably could have sized down a little bit, but between making sure we hit that lateral load and availability of material was our real governing factors.
Did the lateral load, once you have figured out, okay, this was the size that you're going to use, you presumably then calculated your lateral load capacity. Was it close to what you actually got, or was what you found out in the field was still a lot higher than you anticipated?
It still ended up being a little bit better than we anticipated. We had limited data in that upper fill, which is where most of that lateral support came from. So we ended up being relatively conservative for that fill layer, even for our lateral loading. And it just appeared to be in a better condition than we assumed.
Okay. Thanks again for the presentation, Alicia, and same thing to Patrick. More